Okay. So correction from last time. So I made a stupid mistake for preframing. Computation ratio for L0 and BK is indeed so not anti-computation. This computation ratio minus KBK. So last time I seems like I have written like this way. Sorry, this is totally wrong. This is totally wrong. Okay, so be careful. So this is totally wrong, and then thanks for pointing it out. Okay, today I will talk about the most important class of 2D CFT called minimum model. So this is the birth introduced by Belovin, Polyakov, and Zamorozhkov. In 1984. So in the e-learning, I put the file for collection of this collection of the papers, and then even lecture note, I always show the original paper in collected here. I think conformal imbalance and the statistical application to statistical mechanics. It's 1,000 pages, but the first paper is this one. 1984. It's in London Institute. In Moscow, everything started from this paper. So this will give you the birth. This is the birth of the 2D conformal field theory. They just introduced the Biot algebra, minimum model, and so on. And then from then, everything. After that, yes. The strong, how do you say, stream of the explosive stream of the research on 3D CFT started. Yeah, and including after the immediately Cardi wrote a paper on the torus and so on. It's also this cosmic energy. So after you take this course, I highly recommend to read this original paper. It's a very important paper, and then after taking class or after finishing this minimum model, hopefully you can understand this paper. So what is the minimum model? So the Hilbert space of minimum model. Hilbert space of minimum model is indeed consists of a finite number of irreducible representation of Biot algebra. I will tell you what is the irreducible representation of the Biot algebra later, but the important part is this finite number. That's the most important part. So due to this finite number term of irreducible representation, you can determine the correlation function or spectrum or correlation function exactly in this model. So the ultimate goal of quantum field theory is to determine a correlation function or like a spectrum here in space exactly. And in this model, you can do that actually. So this is one of the first instance of the exactly, so sometimes exactly solved model. Solvable model in quantum physics. It's hard to find such a model in general, but in 2D CFT, in particular this minimal model, this you can determine the correlation function here is space exactly. Okay, so that's why very important. And later, so we will see even the so-called Lanage's so so-called CFT correspondence. So given a asymptotical free theory, so in quantum field theory, so people often ask, given an asymptotical free theory, asymptotical free means if you high energy, the theory well defined. And then what's happening IR? So that's the basic question in quantum field theory. And given a Lanage's model in two-dimensional, what happens in CFT? So we'll see in the subsequent lectures, some of the CFT will be described by this exactly solved model in 2D CFT. 2D CFT. That's why we learn to quantum field theory. At IR. Okay. It's called the infrared fixed point, or sometimes called in the first lecture I told you the Wilson-Fisher point and so on. So the CFT is described by the exactly solved model, then you can really understand what's happening in IR. To understand minimal model, so first we'll talk about the quantum family. So we know that the given primary state, whatever, the primary, there's a corresponding state operator correspondence, the primary state, primary operator and primary states, there's a one-to-one correspondence, and we know that the, so H is defined by limit z goes to 0, phi of z acts on vacuum, and we often, and L0 acts on H is of course H times H. And also we know Ln acts on H is equal to 0 if n is greater than 0. Okay. And we know that so if n is less than 0, so we will have highest weight Bernoulli module, whatever. Abelian charge of L minus 1, L minus 1 square, H, L minus 2, H, and so on. So these are co-descendants. Okay. And what is the corresponding the operator is that the you can just easily define the follows. State operator by state operator correspondence, so the you can define phi. Its notation is like this way. Is equal to W. You can set it to 0 if you for the sake of convenience. Minus n phi. So now n is treated by a positive integer of W. Is state operator correspondence 1/2 pi I. dz cw 0 minus w n minus 1 times t of z. So recall that the t of z can be understood as the ln z minus n minus 2 and you can have the mode expansion around the origin, but here we just do the model expansion of t of z around the w, okay? Do you understand? Around w. So that the L minus n acts on phi at the point w. and you can use, so we know the t, so the phi is primary state, so we now assume phi is the primary state, so we have the OPE is indeed given by h phi of w squared plus phi of w. So that this is the OPE, t and w. Plug that into here, you can just do the contour integral. For instance, I hope I don't make a mistake. Seems like I made a mistake. Let me think. I think it should be plus. I think. Yeah, it should be plus. This one, it should be plus. Is there a typo in lecture note? Plus n minus 2. And what I want is the. Oh, it seems okay. Then why do I write like this way? Sorry, I got confused. It looks to me it should be plus. Let me do that. Sorry. So t of z is equal to. So now the model expansion L n z minus w n minus n plus minus 2. And then what I want is the minus n and the plus. And what I want is just acts on z minus n plus 1. Oh, sorry. Z minus w minus n plus 1. Okay. So it looks okay to me. Let's see. Okay, that's fine. So this is okay. And then this is typo, sorry. The first one is wrong, actually, clearly wrong. Okay, so that's fine. So this is okay, sorry. So then, for instance, phi minus 1 of w is indeed given by 1 over 2 pi I. So the z 1 over z minus w. Oh, it's okay, sorry. What am I doing? Sorry, my brain is not working. So w 0 minus 1, okay. Minus 1, which means times z minus w, sorry. Sorry. Why am I doing stupid thing? So times this one, this guy, t5 of w, and then this one counter was 2 here, and you have 1 over z essentially. You do the contour integral, and you essentially get the h phi of w. Okay, sorry. And likewise, if you take minus 1 of w. Selection is correct. You pick this guy. Oh, sorry. So this is what's really happening. Okay, so that's what's happening. So it's, but I mean, essentially L minus 1. So this can be understood L minus 1 phi of w. So L minus 1 can be understood as the first derivative. Okay. So that's the consistent what we learned in the Witt algebra. Okay. So you can just look back to the Witt algebra. And now let's consider the correlation function. with descendant and primary. And then phi 1. So let's consider correlation function. All are primary. So they all are primary. Okay, so they're all primary. And then also note this one is equal to x. Denote. So then we can just plug that one into here. Phi minus n of w x is equal to 1 over 2 pi I dz. So then we can just use the OPE of the opposite. So we take so here CW, but now we just consider the complex plane and the point W here, but the rest of point is Z1, Z2, and Z3 and so on. If you take the contour CW is here, is equivalent to take the rest of the point, Zn, equivalent to take the opposite contour. I mean, depends on the notation, but like this way, it's equivalent. Because I mean, if at infinity, if you take infinity, it doesn't hit the pole, so you get the 0. Okay. So therefore, in taking account the direction of the arrow, so we have the CWI. Yeah, I mean dz. So it's I've been a bit schematic. I mean my expression is not that precise, but anyway, maybe I should put the I here. And then now we have 3 minus, oh my goodness. Okay, let's call W according to my lecture note. Sorry, I'm very sorry. So I changed the notation. W here, and then W is okay. And then we have WI. So this is just OPE of so this is and we define this operation as the L minus N phi of W. So note that L minus N is just can be defined as I, and then N minus 1 times HI divided by WI minus W to the N minus 1 over WI minus W N minus 1 WI. Again, I got confused. Sorry, I think I don't need this N minus 1. I don't think we need this N minus 1, do we? Can anybody tell that? Yeah, I don't think we need this one. I don't think we need. Yeah, I don't think. Let me think. Sorry, my brain's not working. Let's see. I think this, so we just plug that z equal to w, then we will get this is equal to this one, and then we have this guy. Sorry, just my today. Why? Where does n minus 1 come from? Integral parts? No.
The derivative about the z when you doing this signal output.
So derivative with respect to z.
Yes.
Since they have the order of the residue is different.
Okay. So what I'm doing here? So derivative with respect to z. But where does derivative with respect to z appear?
If the residue is first order, then you do not need to be
Oh. I see. Sorry, but I still don't get it. Okay, I see. Now I understand. Okay, you're right. Yeah. So here it's coming from the so Zn over 1 over 2 pi I is equal to f of z is given by but I still don't get it. Okay, so let's honestly look at. So here what we, I see. I think I understand what's going on. Sorry, I understand what's going on. So if you take the pole at the Wi, so you have to substitute. Yeah, sorry, my brain is not working. You have to substitute z is equal to Wi, okay? Wi, so this one is okay, it's just a substitute Wi because it's the first order, but the second order, you have to take a derivative, okay? You have to derivative. So that will give you 1 minus n inside, in front, but you have a sign difference because of you swap 1 minus 1 to n minus 1, okay? That's why you get this one. Do you understand? Sorry. My brain's not working. So you just do the contouring in Wi, so that the plug z is equal to Wi, and that will give you this guy. On the other hand, here you have a second order pole, so that you have to take derivative. Okay, sorry. If you plug n equal to 1, you will get the desired property. So minus 1 is equal to so this is the indeed equal to this one. So that is equivalent to taking the W. Sorry. Okay, so this is the case. Then now, so we have the we can just consider lots of L acts on the operator. So which can be understood as the, just do that recursively. CW, dz, c minus w, 1 minus k, dz, L minus n, phi, w. Okay. That's the how you define the two Virasoro generator negative mode acts on the primary states. And then in particular, we can have that the phi 0 minus n of w is equal to h plus n phi minus n of w. Okay. So here you just add the level. H plus n is a level because the you can just always this has when k equal to 0, this OPE always have something. It's singular term plus h L minus n phi of w z minus w squared and dot dot dot. So even though it's not primary, so the second pole always have the conformal dimension or scaling dimension times this operator. So that then if k is equal to 0, 1 cancel with this 2, and you have a first order pole, and you pick up this one. Okay. Sorry, h plus n. Sorry, h plus n. Okay, so you have the minus n and then dot dot dot. No more. Moreover, so if you have minus 1 minus n of w, you have the so here maybe more precisely you can have just here is phi minus n of w, and then first order pole is also first derivative, always first derivative here. But you have the higher singular term if it is not primary. Okay? If it is not primary, so there is a higher order term, but we just only look at the second pole and first pole, it's always like this one. And the same calculation, recursively doing the same calculation. If you have the so what we are doing is that if you have k1 L minus k2, this will give you the descendant of the primary field acts on H that corresponds to phi minus k1 dot 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 minus kn of w. So this is the state operator correspondence, state operator correspondence. And now, so we can just take a look at the correlation function. Then you just add this operator L over there recursively. Like this way, okay. So therefore, so everything comes from the correlation function primary states, okay. So everything you can just determine correlation function from primary states. Okay. Okay, then so these are called so the phi and descendant is called compound family. So phi whatever phi minus one, phi minus one minus one, phi minus two. Sorry, phi minus two, and it's the same thing of the highest weight representation. Minus one minus one minus one, phi minus one minus two, whatever phi minus three, and so on. So these are called compound family. Maybe I should write down in the right. This is called compound family. Okay, just show you the example of that. This one. So, for instance, if you look at the TZ file WOPE, so this is indeed equal to T of Z phi of W, and this is equal to H phi W Z minus W square and then Z minus W cubed plus H plus 1. So H, so this derivative can act on this phi, okay? And derivative can act on phi, but another derivative acts on this guy, okay? In one of the Z minus W, and essentially you get the H plus 1 phi of W, Z minus W square plus the owner piece. Okay, so this is the OPE, okay, of the descendant. So you have since this is descendant, you have a singular higher order singular term, okay? It doesn't stop by second order, but the compound dimension is H plus 1. Okay, it's H plus level. Okay, level, and then you have this is the first one instance of this guy. Okay, do you understand? And more precisely, I can just write down this one is phi minus 1 and this minus 1. Okay. Any questions so far? Okay, so let's talk about minimal model. So in minimal model, as I mentioned, the Hilbert space consists of finite many reduced representation or highest weight representation of your thorough algebra. And then, so if you have, which means that you only have a finite many primary states. So which means you have H1, whatever called HP. So finite many primary states, okay, and you have a descendants. Okay. But now, so it's not simple Bangor module. You have to somehow do the operation called. You have to throw away so-called null states or singular vectors. And in particular, so we will have the OPE. So in this case, you have an OPE. So if you have the phi 1 of Z and the phi 2 of 0, then what you have is usually OPE takes the following form: the sum of yeah, I mean, okay, and z hp minus h1 minus h2 plus k, and then phi p of k. Sorry, so I think I should also sum over. So usually OP takes the following form. So if you have a two primary, and then so it's expanded by the other, so some primary with descendant, okay, with descendant of primary. So this is a form, and OPE, and since the correlation function of descendant can be constructed by primary field, so we just need to talk about, we just need to consider only the correlation function of OPE. And in particular, so this capital K, so this is capital K. Capital K can be understood as K is equal to sum over I, Ki. I think I should write down this is minus K. So anyway, it's okay. I mean, so what I meant here is the phi p of the notation K is indeed phi p minus K1 minus K2 and dot 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 minus Kn. And a capital K here, so I should distinguish. Is sum of Ki. So it's a level of the descendant. So if it is a finite many primary field, we can just do the OPE to get the to reduce the number of the how's that operator. And since descendant can be or correlation function with descendant can be obtained by primary field, everything reduces to the OPE of primary field to determine the correlation function. That's the power of the nice characteristics of a minimal model. So the important thing is there is only finite many primary field in the minimal model, and then so now from here we will use to define so-called irreducible representation of Birational algebra. So Bellman module is not irreducible in general, and there's something called singular vector should appear in the spectrum, so we need to throw it away to get the irreducible representation. So that's what are the singular vector? Singular vectors on the. So we just start with the. So as we learn, what is the Bellman module? So you start with H, and you just act on. I mean, I already know. Write down many times -2 H, and then. N-1, N-2, H, N-3, H, and so on. So this is a Bellman module coming from, or highest weight representation coming from primary state. Okay. But here, so in the descendant, there is so-called, so usually people here write down H, C. So H is the highest state, conformal dimension primary state, and C is, of course, the central charge of the Birational algebra. And in here, it often contains the singular vector or singular states or vector. So the chi inside BHC such that this acts is annihilated by when n is greater than 0. It's like. So this is called singular vector. So singular vector. So if you have any state, so this singular vector is orthogonal to any state in BHC. So any state in the Bernoulli module can be understood as like this way. And you just take the inner product with chi, the singular vector. And if you take the, this is indeed opposite, so H, Kn, K1, and chi, star. Or dagger, whichever you call it. Yeah, dagger. Then, so here K is all assumed to be positive. So therefore, this guy annihilates chi, right? So this is 0. So therefore, so the singular vector is the orthogonal to the all states in Bernoulli module. And moreover, so in particular, so you can understand the chi, and the chi is equal to 0. So this is called null states. So if chi, so chi is a singular vector, all the generator K1 L minus Kn of chi is also null. Also all null. Null states. Can you see that? Can you see that? Look, let's pick for instance, how about this one? So it's a simple exercise to do. Let's pick this guy and take inner product. So let's call this is whatever psi, whatever z, xc. And we want to see xc, and c is equal to chi L1, L minus 1, L chi. Okay? Do you agree? And this is equal to chi 2 times L0 chi. Do you agree? And this is 2 times h plus some level n. So level n times chi of chi, which is equal to 0. Okay? You understand? So likewise, you can just take the inner product. You can easily see that at the end of the day, so this n is the level of this chi. Okay, at the level. So this is the. So you recall that the level is 0, 1, 2, 3, and dot. N is the total. Yeah, like this way, total number. So that. I mean, instead of k, I just use n here. So total, how to say? The sum of this lowering operator, the model of model of the lowering operator is equal to n. Okay. So therefore, likewise, I mean, you can just take an inner product at the end of the day. So to do the computation ratio of Virasol algebra, one can check this is indeed true. It's a null. So therefore, so given whatever, okay, so I think it's better to use this one. So So ln is of course -1 to the n of h, and so on. So it's same operation to the n minus 1, l minus 2, and h, and so on. And this, so you just can construct. So suppose you can construct the linear combination of these vector. Using linear combination, you can construct chi inside here. So here you can just construct a chi, which is linear combination, some number, whatever, ci, and vector. So these are whatever basis bi. Okay, so this is a linear combination. Just ci is just constant, and you can construct this one. Now, so you can just act Virasoro algebra L minus 1 chi. This is also null states, and we know -1 square chi, and L minus 1, L minus 2, chi acts on it. These are all, you can just check all null states, okay? As I mentioned over there. So you can easily check by using the computation relation Virasoro algebra. So here, again, it's Virasoro algebra acts on all null state, okay? So this is a submodule. So this chi, from chi, you can just act like a lowering operator or whatever, creation operator, whatever you call it. Cube chi, and then L minus 1 square, L minus 2 chi, and then whatever, L minus 3, and chi, and so on, dot, 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 dot. So therefore, from so you start with h, and there's a bound module, but now if you have a chi, so at the level, at the level of n, you have a null state. From null states, you can just act on this. There's descendant. If you consider descendant of chi, you can have some submodule of Virasoro algebra. In total space, Virasoro algebra acts on. But if you look at the descendants of chi, if you only look at the descendant chi, also Virasoro algebra acts on it. And all states are null here. Okay? And this is, the whole thing is called Bauman module, but this submodule is called, we call JCH. And JCH is indeed, they consist of chi is all null, and then the conform family of so this is the submodule of and of course, we are interested in some in physically we are interested in unitary theory, and then we don't need some null state. So we just consider, so this is null state, and this is submodule. So this is submodule of Bauman module. Okay, it's called submodule. Of Bauman module. And we just want to throw away so you just consider quotient representation, quotient module. So this is the is called irreducible representation. So this is irreducible representation. So in minimal model, so you just have finite many primary state, as I mentioned. So as I mentioned, finite many the irreducible representation. But from each primary state, you can have a Bauman module, but you throw away null states. Okay, you throw away null states, and take only the inner product of the norm of the states is non-zero. So that's the operation you need to do to get the irreducible representation. So the question is how you get. So when so therefore, so each time, so given the primary state, each time you have to throw away this new state. Therefore, we need to know when this singular vector show up. We need to know when this singular vector show up. So to understand when this singular vector show up, we just take the inner product of this the same level. For instance, let's look at this guy. So when the singular vector show up in this level 2, let's first take a look at the. So the reason why level 2 is level 1 is too boring. So I just want to. Yeah. Okay, so at level 2, so we just take the inner product. So when this level 2 has the singular vector, you just consider matrix, the following matrix. So L2, L minus 2, H. So H. So you just take the inner product of each states, and okay, so you just need to do the computation operation. I mean, it's good exercise to do. I mean, here to essentially what we need. It's too boring to do that. So yeah, I mean, I just demonstrated one example. So this is the minus 2 to 4. L0 plus C over 12 is m squared minus 1, right? As far as remember. So therefore, this 2 times so 1 over 2, yes, C over 2. Okay. So therefore, here the matrix is 4H plus C over 2. Do you understand? Okay, and then we can do the same operation. I mean, L1 squared, L minus 2. So you need to know what's the consequence. So this is indeed 6 times L naught. So you can just do the computation operation. Yeah, I mean, you can just check by yourself. This is 6H and 6H. And then we have to know that the computation relation between L1 square, L minus 1 square, and this is equal to to be honest, this one is a bit tricky. Yeah, so this one is equal to 4 L naught plus 1 plus 2 L. So you can just check this computation relation by using Pearson's algebra. It's just a straightforward exercise. So that here you have for h plus 1 plus 2h. Okay. So this is the matrix you get. Okay. This is the matrix. And take determinant. And take determinant. So let's erase. So take determinant, we will get, so determinant of this matrix. So let's go M. So when determinant M is equal to 0, singular vector will show up. Okay? So that's easy to see. You understand? So you have a null states. Okay? So linear computation of these two states will give you some null states. So then this is equal to indeed 32 h minus h11. The notation is c, h minus h12c, and h minus h21c. And then, as you can easily see, so here h11, c is equal to 0. And then h12 and 21c is equal to 16. It's just a plus minus 1 over 16. It's just a quadratic equation you have to solve. Okay, so that's actually first done by it's before because it's this one is already computed by before BPZ. It's done by Katz in 79. Katz is a mathematician, but he actually created the theory of infinite dimensional Lie algebra. Nowadays called whatever, affine Lie algebra, Katz-Moody Lie algebra, and so on. So now, let's see what's going to happen. So first, let's look at the solution h11 equals 0, which means that the h is equal to 0. H is equal to 0, then this means that the so h is equal to 0. So this means that let's look at the L minus 1 vacuum is equal to 0. So let's take a look at it. I just got confused by a bit more. Oh yeah. So as I mentioned, so L minus 1, 0, I already showed, right? 0 is equal to 0 to L0, 0, which means 0. Do you understand? You get null state. Okay, so therefore, if the conformal dimension h is 0, then at the first state you already have a null state. Okay, so this is if and only if. Okay, so then if there is a null state, as I mentioned, if there is null state, if you act on L minus 1 acts on chi, this is also null state. Okay. So therefore, if this is L minus 1 of chi, 0, and this is L minus 1 acts on 0. So this is also null state. That's why, if there is a null state of level 1, even at second level, there must be a null state. Okay, at the level 2. Okay, that's how you interpret it. That's why I wrote this 1, 1. I will tell you what does what this one means later. If you multiply them together, 1 times 1 is equal to 1. That's why it appears in level 1. Okay. On the other hand, so you have this solution 1, 2, and 2, 1 is really the so when H is satisfy this condition, there must be a 1 null state that appear in the level 2. So that's what it means. So, and the Katz notice that so if it's okay, so how did I explain it here? Suppose so this phenomena really I mean just show you just want to show you the instance. Suppose there are null states level n is a null state, and again you have n plus 1, n plus 2. I mean it's already too boring for you guys. I don't know how many times I wrote down. And as I recall, so there's a number of null states indeed. P coming from chi is actually P n plus level n. Then at the level capital N, you have the so you have a number of states is so this is this is level, and this number of states is 1, 2, and at the here is p times n minus 1. Okay, so this p is partition. Okay, as you recall. So as you recall, oops, I shouldn't erase this part. So therefore, so given if the level of small n, if at the level of small n there is a 1 null state appear, then as a descendant of p, the number of the null state is indeed p of n minus capital N minus n at the level capital N. So that's. Okay, so this phenomenon is ubiquitous in this computation, and then Katz noticed that the following: the determinant of matrix. So this is matrix. Here more precisely, this is 2 CH in my convention. Okay, this is CH in my convention. It's very strange. Okay, CH in the convention. Katz noticed that determinant n, CH, is some number, some constant alpha n, some number. That's product of RS in less than n, and then H minus H R S C P n minus So this is called Katz determinant formula. This is called Katz determinant formula. Okay, okay, so the reason why you have this power p here is power p here is really, the number of states coming from this new state upstairs is indeed the partition of n minus capital N minus n, and the small n is indeed the product of R and S. Here is also same. So product of 1 times 1 will give you the new states in first level. That will give you the new state in even second at the level of level 2. And on the other hand, so you have new states appear, new states appear, level 2, and then twice. Okay, twice. So therefore, always you have the, new states appear when R times S is equal to the level. Do you understand what I mean? Do you understand? Are you guys following? And the question is, what is the formula for this HRS? This is the usual. In CATS did the computation. It's not so difficult. Nowadays you have a mathematical and so on. It's easy to see once you compute a few levels, you can easily see the pattern. And anyway, so the CATS did this computation late 70s. Found the general formula. Okay, I will give you two expressions. Both are important. So what is the formula? So for this one, so two way of writing. So H0. Okay, H0. Yeah, let's follow this direction. R alpha plus S alpha minus square. It's just quadratic. And then we have H0 is indeed equal to, this is equal to 1 over 24 C minus 1. And alpha plus minus is equal to square root 1 minus C plus minus 25 minus C divided by square root 26. And then, of course, already erased. No, great. If you plug R is equal to 1 or 2, you can see this is equal to that one. You can check. So now the expression is given by the following. Both are important. Both are useful. And you have to use in the homework later. Both expression. So here, so we express C is indeed a rational number. If C is like this way. Okay, so if so plug this one into here, you can just check this is equal to this one. If P here P here P is a secret assumes some positive integer, but you can just assume P is some real number if you want. So sorry. So this, if you write, central charge like this. Okay. So both are useful. So you need to use both. There's a typo. There's a typo in my lecture note. This M has 2 branches, but it should be P. Okay. Anyway, so So what does it tell us? So here, so if you look at the when c is equal to 1, so let's look at c equal to 1. It's an important part. So when c equal to 1, so you just take a look at the here. So the h0 is 0. H0 is 0, and then this part is 0. And 25 minus c is equal to 24, and they cancel. You have plus minus. Okay. So what's left is this. Okay. So therefore, HC HRS of c equal to 1 is indeed 1/4 and alpha plus minus s squared. Is it correct? Yeah, it should be correct. Okay, so everything quadratic, and we assume that R and S here, R and S are positive integer. Okay, positive integer. So therefore, so when this condition is satisfied, null state will show up. So I mean, high h, the conformal dimension is satisfied. This quadratic divided by 4, quadratic number divided by 4, null state at level RS, R times S. So that's what it means. So on the other hand, so another interesting part is c equal to 0. C equals 0, what's going to happen is when c equals 0, so you can just plug this one is p equal to 2, okay? P equal to 2, c equals 0, okay? And plug that one into here, what's going to happen is h, so c equals 0 means the p equal to 2, and the h rs of c equal to 0, 3r minus 2s squared divided by, so my brain is not working, 2 times 3 times 4 is 6 times 4 is 24. Good. Okay, so therefore, if this condition is satisfied, again, the same thing. Null states will show up at the level of RS. Otherwise, irreducible. So both module irreducible. Okay. Otherwise, one more module. Okay. Okay, so that's what's really happening. And then the relation between C and H and this Katz's determinant formula is written in the figure in the lecture note. I mean, you just need to solve this equation. I mean, it's a really boring procedure. But anyway, but I mean, it's a super easy procedure, and you just have a curve like something like a. I mean, I'm not sure if I'm going to successful to write down C and H, and C equal to 1 is here, and then so C equal to 1, something special occurs. Something special occurs, and what we're going to happen is indeed. I'm not sure if I'm going to be successful. This H is equal to quarter. Okay, let's use the color chalk. quarter, and then I think it's a bit below it's better. So and then so quarter. Okay, this is 1. And then you have something like a curve, like something quarter curve, like this way. And then it's very difficult to write down everything. Okay, I think it's okay. Okay, so sorry. Let me try in the case. This curve, and also you have there's a 1 here, one coming from like this way, quadratic curve like this way. And then so the curve is something like a whatever. It's hard to draw, but nonetheless, let me try. So like this way. Important thing is that the here. So here is actually there's an intersection here. That will give you 7/10, and here intersection here is given by 1/2. Already my drawings already show that this is horrible drawing. So this is indeed 1/2. Let me a little bit. Let me a little bit cheat like this. Okay, so the cheat here. So this is the important thing is everything rational. So intersection, everything rational. This is 1 here. So important thing is that the curve is bounded by the c equal to 1. So that's the most important thing. And as I recall, as we mentioned, so the new state appear quarter, and then r is equal to 2 is r minus s is equal to 2. I mean 2 squared is equal to 4. 4 but 4 is 1. It hits 1 here. Okay, it's here 1 here. So it's quarter times n square will appear on this here. It's always bounded here. I will tell you the reason later. And of course, and also if you look at the here, you have you start with 1/3 that satisfies this condition. I think this is this part is equal to 4. Okay. Sorry, not 4. 3, sorry. This part is 3. If this is 3, 3 squared is 9. 9 minus 1 is equal to 8. 8 divided by 24 is 1/3. Okay, and so on. Okay, and always the rational number appear. And also the important thing is if you look at when this curve cross, always this part is rational number. Okay, rational number. That's most important thing. And because the minimal model fits into so-called, we will see later, rational component fit theory. The reason why it's called rational component fit theory, always central charge is rational. So when they cross each other, if you look at the central charge, always rational number. That's the most important thing. Okay. Okay, so let's stop here and then take 10 or 15 minutes break. Any questions? So we assume always. So we just consider level n. So you have a primary, not primary, the null states. or singular states, whatever you call it, singular states, then this can be understood as some linear combination of whatever, Ci, Bi. Okay? And always this Bi, so Bi is, I mean, one of the instance n1 minus n, the h, right? B1, and so on. And those things always, if you, as you recall, if you look at the OPE of the phi minus n or so on of W and T of T, then this is, of course, it's not the primary, so it's a descendant. So you have a singular term, but always you have h plus n, phi minus n of W divided by z minus W squared plus dot dot dot. And this h plus n is really the component dimension of this Bi. Do you understand? So, moreover, you can just have the bunch of whatever, minus k1 to minus kn, kl, such that the n is equal to sum of ki. I runs from 1 to l. Okay? So this is also okay. Then, so the sum of n, this is always, you can check by yourself or whatever, k1 to minus kl. Descendant, if always appear h plus level. H plus level. So that's a component dimension or scaling dimension of the descendant. Any other questions? Okay, let's take a break. So graded homework is here. So please pick up if you submit by hand. Okay. Please pick up. Should I dictate the name? Xu Hongshui, Cheng Feng. I'm sorry, I cannot dictate his name. I don't know. I'm sorry? Yeah. Both. So the beginning of the when I What's the compound dimension of the boson field? What is the compound dimension?
One. Boson field. No.
This is so this is dimension. This is the compound dimension which is zero. This is one. When you plug that one into which is zero. So this one. You understand?
I confused about
你对一个周期的东西加一个负 EF， 它啥也不是。对，也就是路径机，其实它本来就有这种东西，所以时间那样写的会很一些。然后，那为什么总电说系数？F 是非粒子数算一个单，比如说我们举个简单例子，就是单倍粒子来。 它是作为它后面的算如果你只有波色词的话，就等于1，所以这个东西就等于不算是一个算是一个负1的 F 词号，然后你可以用 C 把你对了，然后 A 再一个 A 啊，可以用那个基础展开。它会正好在那个你需要打多次的地方产生一个负1的法律效应。可以上一个知道你算出来，然后你变成那个时间，然后发现它那个计算，但不知道为什么这个。
Okay, shall we start? So some students are not back yet. So the homework, I already forgot what kind of homework I gave you, but my computer is not working. I don't know why. It doesn't open my file. So one thing I have to mention that in free body you have canonical quantization, whatever pi and phi is equal to or for t and x and then phi t and x prime is equal to some number times x minus x in prime. Okay. So from here you need to get the computation ratio ak, and then a dagger m is equal to delta k plus m 0. Do we have some constant here? I think k times this one. Is it true? Okay, k times. So to get from first line to second line, you have to perform the Fourier transformation. So many people, many people just plug this ratio into here, and the model expansion here, and show this one. This is not right way to do that. This is not right way to do that. I mean, so you have to perform really Fourier transformation to get this computation relation. This is very basic in canonical quantization. Always you have to do. Just the reason why you learn Fourier transformation is to, one of the reasons why you have to learn Fourier transformation is to get the canonical quantization correctly. Okay, so that's the thing. Okay, and another thing is that the some students are taking lots of courses and lots of and it seems like lots of homework this semester. Somehow young professor wants to give lots of homework like me. I'm not young, but anyway, so so some students may want to have the deadline on Sunday because she or he can do the homework weekend. So just let me take a vote. Okay, so if you want to have deadline on Sunday, please raise your hand. On Sunday, every week, Sunday, every week.
The next Sunday, or this Sunday.
Not this Sunday, it's too early. There are only 3 days, right? It's impossible. It's impossible. So if you're on Sunday, just raise your hand. 1, 2, but so only registered students raise your hand. 1, 2, 3, 4, 5, 6, 7. Just raise your hand, please. I cannot count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Want to keep the deadline as it is on Thursday. 2. Okay. So I will change it to on Sunday. And if you want to submit on Sunday, only PDF submission allowed. Okay. I'm not gonna be here, or just went to Janwan and give the by hand Shandong over the Shandong's office on Sunday. Okay, so I will change it to every Sunday. Okay. But anyway, so it doesn't change. Okay, so I will change it to on Sunday in that case. So what else? What else? Somehow my laptop does not open my lecture note. I don't know why. It's crazy. What happened to my laptop? Oh, finally. Oh, it opens. Good. Okay, let me continue about minimum model. So now, so important things I also emphasize only rational number of the central church here. But if you look at the compound dimension here, also it's rational number. It's also rational number here. Okay, so both central church and the compound dimension, it becomes rational. And so the minimum model, so we will see in later, so minimum model fits into the class of rational compound field. Okay, so let's move on. How do you pronounce his name? Jiangji. So, is there any friend of Jiangji?
I guess he is.
Oh. Okay. So he will take care of it. Okay. Where are we? So we talk about the Kapp's determinant, and now let's talk about minimum model. So developing Zamochkov noticed that the all correlation function can be determined by the differential equation. So now let's go BP's equation. When the cut determinant becomes 0. So let's look at the example. So for instance, so we know that so suppose chi as a level 2, chi is singular vector. And then chi can be written as with a loss of generality, so we can just written as a like this way. Then we can just have, so we want to determine what A is, and then of course you can just use the cut determinant formula, but here it's very straightforward. When this this chi has to be 0, L1 acts on chi has to be 0 by definition, and then we just apply this kind of stuff. Anyway, so it's too straightforward, but it just do the you guys need to do the calculation. H, and then what you get is this one is 3 L minus 1 H plus A L minus 1 2 L0 plus 2 L0 L minus 1 H. Okay, this is the just straightforward calculation. And this will give you the number A has to be minus 3 over so A is equal to this one, okay? And you can get the body of H also too. So by applying L2 chi has to be 0, and then you just do the again same computation L2 L minus 2 H plus A L2 L minus 1 square H is equal to 4 L0 over C over 2. So this is very simple. And then this is also 3A times 6 L0 H. So therefore from here one can get H. C, the relation between C and H. C is equal to 2 minus 6AH minus 4H, and this is equal to 2H 5 minus 8H over 2H plus 1. Okay. So this is a relation between C and H you get. And then you can just solve this quadratic equation. So H is equal to, just the same as before, 5 minus C plus minus square root C minus 1, C minus 25. So this is how you get the relation between central charge and H. Okay? And when this happen, singular vector show up. And now let's look at the consequence of this one. So this state operator correspondence, there must be a state operator chi of Z. And look at since the chi and any states are orthogonal, so we know that the chi and any state, any state, maybe whatever state, psi is always equal for any psi in bound module CH CH maybe, CH module. So this end up with the decoration function Z and X of whatever. Primary state is also Z in the theory. Okay, product. And then now, so apply the construction of what we used. So since it's a descendant, we can just apply this differential operator, 3 over 2 to h plus 1. So a is now minus 3 over 2 times 2h plus 1. So you just apply this operation. Acts on the primary. Okay. So then, so we know that the L minus 1, we already showed at the, what was it? At the beginning of the lecture when my brain is not working. So L minus K minus N is equal to N minus 1 HI WI minus W to the N minus WI minus W N minus 1 WI and sum of I. So that's we derive, so just plug that into here and you get the differential equation. So, and in fact this is called BP's equation. This is called BP's equation. Plug that one into here, and what we get is sum over I is equal 1 to the n. So x is assumed to phi. Now I use Zi. Then 1 over okay, so that's what you get. So here I use the, of course, the. Anyway, so you understand. You understand. I'm not gonna explain. It's a bit. Maybe it's a bit too slow today. Phi of z of x is equal to 3. Okay. And suppose, okay, so this is the equation at the including when the this h and c satisfy this condition. H is the, of course, the component dimension of this primary. Okay. Now suppose the x is equal to just this primary state itself. Okay, then what we get is z minus d minus w. Okay, that acts on and we know this is equal to we know that this is equal to z minus w. To h divided by some constant, okay? Constant divided by this. And you can just easily check this is also satisfied. Should I do that? Kind of. So do you want me to do? It's kind of straightforward. So let's do that in that case. So if W acts on here, what we get is 2h, right? 2h and plus h minus 3 times 2h times 2h plus 1 divided by 2 times 2h plus 1. Do you agree? Are you guys reading? Do you agree? Partial W acts on here, you get the 2h, right? Do you agree? And this one is as it is, but here partial z square acts on 2h, acts on here, you get the 2h times 2h plus 1. Okay? And you get this one, right? And also the degree of the singularity is same. So first derivative and this one, and the second derivative nothing. So it's the same. So then you can see this is equal to 0. Okay? So therefore 2-point function is trivial. Let's look at 3-point function. Okay, so here, so you have a different primary field, phi 1 and phi 2, different primary field. And now, so we know that this one by component transformation, component invariance, we know that some constant z12. Okay, I cannot write down like this way. In that case, z minus z1, h2 minus h minus h1, and z1 minus z2. H minus H1 minus H2 Z minus Z2. So this is you did to derive. You derived in the homework. So this is, and then you just apply this is equal to n equal to 2. Apply it into here. Then what you get is the this is homework to do. Homework to do, so this is homework. So this has to satisfy the following. So it gives a relation between H2 and the H1, the relation between H1, H and H1 and H2. So this is homework. Derivation is homework. Homework plus 1/3 H plus H1 minus plus plus minus 2/3 H squared plus 3h h1 minus 1/2 3h1 2 plus 1/16. So this is the relation you obtain. Just plug this one into here and then solve the equation, and then you get this thing. Remarkably, what we get is indeed, so if H, so we know H is equal to H12 or H21. We can set H12 or H21. And suppose H1 is equal to HRS. And this is all homework. You need to check in the HIRS. Then, indeed, so the plug that into here, then what you get is H2 is equal to H R S minus 1. So this is there's a plus minus ambiguity here, or H R S plus 1. So So there's a plus minus ambiguity here. We'll give you two choices. Plug these values, so this is all homework, to here, into here. I don't want to do that on a blackboard. Into here, H2 is indeed equal to these primaries. It's amazing. So this means that the following. So if you have two, so you have the primary H12, there is a HRS to the corresponding RS of Z. So you have the state operator correspondence. If you take the fusion, so-called OPE or OPE of this one, sorry, 1, 2. No, I don't need to. I mean, it's a fusion. It's called fusion rule. Phi 1 times the phi RS. Then this will give you the phi. So this means the conform family of this thing. So this means that if you take OPE of phi 1, 2, Z, and then phi RS, W, then what you get is sum of, it depends on the, so the one I have written down in the beginning. It depends on conform dimension and so on. So essentially, this one is equal to plus phi r s minus 1 of w divided by z minus w. H R S minus 1 minus H R S minus H 1, 2, and plus phi R S plus 1 of W Z minus W H R S minus plus 1 H minus R S minus H 1, 2. Okay. And this has higher singular term will show up as some coefficient show up. In this case, probably 1. It's multiplicity 1. Yeah. And then this higher singular term is indeed show up as a descendant of these guys. Okay, these two guys. The higher singular term, I'm not gonna write down everything, but descendants of these two guys. So that this is operator algebra, can be understood. It's in some sense this can be understood as what you learn in quantum mechanics. It's like this way. So it's more like this way. So in spin 1/2, in some sense, this is like this way. So if you have a spin 1/2 states, spin 1/2 times spin 1/2 is spin 1 plus spin 0. So that's what you learn in quantum mechanics. How many of you knows about this relation in quantum mechanics? Okay. Most of people know. So the plus minus times plus minus is will give you, so spin 1 is found by plus plus and plus minus plus minus plus and minus minus. But on the other hand, here it's bound by plus minus 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 plus. Okay, it's one dimensional. It's like this way. So it's more like it's really like a tensor product decomposition. Okay. Likewise, if you plug H21 here, H21, and then what you get is the following. I mean, it's just the same thing. Okay, so like this way. So the different way of, I mean, it's reasonable, right? So if you have an increasing one, if you have 2 here, you have a plus minus shift. If you have 2 in the left, you have a plus minus shift in the left. Okay, so that's what this 3-point function analysis will tell us by solving BPS equation. Okay. So how the operator algebra arises from the this BPC equation will tell us this operator algebra in particular. So if you plug into the 1, 2 here, 2, 1 times 1, 2 is indeed give you the only 5, 2, 2. Okay. So in general, so I'm not going to write down everything. In general, you have 2 primary generated by R1, spaced by R1 S1 times by R2 and S2. And if you solve this 3-point function, one can just show the fusion rule. So it's the compound family. I'm not going to write down everything. I'm not going to write down everything, but the sum of condition K and L. Phi K L. So you can just show. So this is called fusion rule. So given so here the primary state is with compound dimension R and S cross the algebra, which means if you just multiply them together, you get another primary state and descendant. Okay. So that means they form a cross fusion rule. Okay, so these primary are very, very special one, which means. But in general, you have infinite many compound families. So, but the minimum model wants to have the finite many. Okay? Minimum finite many, this kind of stuff. So the question is when. So R and S are integers. And when this component family, like this, of this primary operator are become finite, the question is. Then now we will see the following. We will see the following. So now, so you have a diagram R and S, and we have the dot here, H11, which is trivial thing. 1, 2. Like this way. So this R and S. So when they are integers, so there are primaries. Okay? And then so let's yeah. And in fact, so let us consider this tangent theta. So HRS can be indeed written like H0 plus 1/4 delta square alpha plus square plus alpha minus square. Alpha plus minus I have written there over there, so I'm not going to write down. And then I just take the following slope. Okay, maybe let me, unless I okay, good. So this is theta. So theta is tangent theta is indeed alpha plus divided by alpha minus. So this is the definition. Alpha plus and alpha minus I have written. I'm not gonna write down again. It's determined by okay. It's determined by central charge. Really determined by central charge. Anyway, so let me get okay, central charge. And then what is delta? Delta. So this is exercise. This is homework to show that to show the compound dimension of our HRS is different, and delta is indeed the distance between them. So RS between this line. So this is the exercise. So this is a homework. So just write down this compound dimension in terms of alpha plus minus and delta. So delta is the distance, the shortest distance to this line. Okay. This is exercise. And now, so usually so this is indeed does not hit. So the usual so generic central charge C. So this line, so yeah, this line is given by the in the central charge. So generic central charge, it doesn't hit this point indeed. On the other hand, however, when C becomes special, it can hit some point here. So now this point delta becomes 0. Okay, delta becomes 0. So therefore, significantly, so recall that the HRS so this is indeed equal to H0 plus quarter R alpha plus S alpha minus square. Okay. If this hits here, delta becomes 0. Okay. So therefore, there is no contribution here for compound dimension, which means the same as R equal to S equals 0. Okay. So therefore, this point can be identified this point. Okay. Do you understand? So therefore, everything becomes closed in this square. Okay. So all the primary are just repetitive. Okay. So therefore, everything, infinite many primary states shrinks to finite many when this line hits to the point. That's what the Belavin-Polakov Zamolchkov found. and this is give you significant sequence. And then when this hits a point, it's called minimum model. Okay, why is it minimum? Because we have a minimum number of final primary field. Okay, you understand? So now, so when this line hits the point, we have a finite many primary field. Okay, let me move on. So when it hits, you can easily see. So when it hits, is of course this slope is rational number, right? Rational. It becomes rational. So therefore, you can just have two integers, positive integer co-prime, p and p prime co-prime. P prime alpha minus plus p alpha plus c. So this when this is condition satisfied, so you get something special happen. Of course, when this is the case, HRS is equal to HR plus P and S plus P prime. So in other words, so left hand side becomes the only matter mod P, and right one is mod P prime. So modular P prime. So this is what it means. So this repetitive compound dimension, and everything shrinks to the this square. Okay, and so therefore it becomes finite many primary field. And then so when this condition is satisfied, when this condition is satisfied, central charge has to be 1 minus 6 p minus p prime square, and then pp prime. HRS is equal to p prime r minus ps square minus p minus p prime square divided by 4pp. Okay, so then and remarkably, so not only this one, but also the symmetry property I show up. H. So this example, what we have. So this is I don't know which one is P and which one is P prime. Okay, I think suppose RS, all right? I have an RS. I think this is P and this is P prime. So this is 1, 2, 3, 4. 4P is equal to 4, and P prime is 1, 2, 3, 4, 5. P prime is 5. I hope this is correct. Maybe P and P prime are opposite. I don't know which one is correct. I'm not careful about the. But somebody very quick mind can tell, right? Which one is correct? Yeah, it should be this should be P, yeah, because R plus P and S, yeah, this is correct. And furthermore, if you use this formula, we observe RS is equal to HP minus R and P prime minus S. So this is symmetry property. Symmetry property. So which means that this point is the same as this point. So this point is the same as this point, right? So this is PP prime. Yeah, PP prime. And this point is the same. Yeah, I think it's correct. So this point is the same as this point. This point is the same as this point. Yeah. So you can just identify. Right? I think I'm correct. Yeah. This point identify this point identify this point identify this point, and so on. So that's very symmetry property. So this symmetry property will give you phi r s is equal to phi p minus r and p prime minus s. And phi rs is, of course, r is less than 1 and p and 1 s. Okay, so do you understand? Any questions so far? This is a very important point. It's a very important point here of minimal model. Okay. So therefore, if you impose this condition, and here, so the only finite many, so the p minus 1 and p plus minus 1 divided by 2. So only, so this is equal to number of primary here. And this minimal model is called, my notation MPP prime. So my notation, I call it this one. And then so you have a closed form again. So here, fusion rule is really close infinite. So I mean, it's the same thing. Sorry, I think it's the same thing here. But the fusion rule can be written like this way. I'm not going to write down K and L. So there must be some condition. K are correlated by R1, R2. L is correlated by S1, S2. And a bit S1, S2, and which is written in lecture note, but I'm not going to write down. It's just complicated. But however, if you impose this condition, now you only have a finite remaining list. So you have to impose up to some like a condition, like a you have a condition like I mean, so this one can go up to p and p prime. Okay, p prime. So the algebra, the OPE algebra or fusion rule, fusion algebra or Fellender, it's sometimes called Fellender algebra, are closed by in the finite many primary field. Any questions so far? So now we are talking about the unitarity. Unfortunately, 15 minutes. Okay. Okay, I already read, so I'm sorry. So we have the HC, and you have C is equal to 1 here, and you have here, and you have like a curve like this one, right? I already erased, and like this way. So this is equal to quarter, and C equal to 1, and so on. And now, so so unitarity. So we physical theory should be unitary, but and we would like to understand. So Kant's determinant also tell us something about the unitarity condition. Um, so yeah, it's very difficult to explain. I mean, sorry. I mean, I think. So as I mentioned, so Cox determinant is something like a determinant m n ch, and this is some number, the product of h minus h r s c, and p n minus r s, and r and s is less than is it correct? I really forgot to write down. What is? I hope this is correct. Okay. What was it? I already forgot. Yeah, it's correct. So as you can easily see, so if you cross this HRS curve, so if you cross this HRS curve, the sign will change. Okay. In particular, here I have written H21. Should I write bigger? And also here you have the H. I have written something like H31. I have written H31. And then, so when you cross this curve, you can easily see the sign will change. Okay, sign would. So when you can just agent. So there's the H and C, but the component field theory. Once you change component field theory, the change of value of C will change, and also the primary field will change. Okay, therefore. When you cross the line, the sign will change. However, this region is intact. If you are sitting here, the determinant wouldn't change. Okay, the sign of determinant wouldn't change. Okay. This will tell us something about the unitarity condition, and then I should mention that the So when h equals 0, sorry, I just got confused. So how do you? Sorry, I forgot how to show. Sorry, give me some time. So in this region, okay. So let me give you some conclusion. So here, so if C is greater than 1, so this is unitary always. So I have a poor management of this section, and then BCH is irreducible always. Irreducible because the first you need to show. So the proof is to first this HRS curve is occurs when the C is less than or equal to 1. And second, Katz's determinant is always positive during this region. Katz's determinant is always positive. Is positive. in this region, in this shaded region. And 3 is this ground matrix Mn, Ch, of course, is positive definite. Positive definite. So you need to show this one. So then all the states, all the states has to be any state. If you show this one, any state of psi in bound module CH, you can show psi and psi is equal to or is greater than 0. If not and then the equality is greater than equality holds only if psi is equal to 0. So this one, if you show this 1, 2, 3, you can just show this unitarity. And unfortunately, I cannot explain very well at this moment because I forgot everything, all the argument. So, but anyway, so it's just if you step, you can just show that the curve is always bounded by c is less than or equal to 1, and then you can just 2 and 3, you can show this unitarity. So I just give you the conclusion, and then what about this one? So as I mentioned, so as you cross this curve, the sign of Katz's determinant will change. So therefore, you have to be careful about the more careful analysis needed to get rid of this negative null state and so on. And then just give you a conclusion. So the unitarity occurs when for C less than occurs. I just give you a conclusion. P and P plus 1 when P is equal to 3 and 4. So this one is called unitary minimum model. So this one happens when P prime is equal to P plus 1. It's just next to each other. Okay? So if you plug P prime over there, you will get this one. Okay? So therefore, so I call it this one is P and P plus 1 is equal to MP. So this is called unitary minimum model. But in general, you don't have the unitarity. So general minimum model P and P prime generically not unitary. It's very important. So it has some negative norm states. On the other hand, here, when P prime is equal to P plus 1, it becomes unitary. Derivation is given by, I already give you in the reference here, given by whom? I already forgot. Presumably Cardi? I don't remember. Yeah, Cardi. So this unitarity is given by Cardi. Yeah. And then, so but non-unitary minimum model is also important. So one example is Lee and the Lee-Yang model. Yang model. Famous Yang, whatever. In Chinese, like this way. Lee-Yang model. we will see in the subsequent lectures. Sorry, so the last unitarity I was sloppy. We'll explain next time because due to constraint and so on. Yeah, so here I just mentioned that the unitarity only occur P prime is equal to P plus 1. And next time I will talk about some character and then move on to the explicit model of the unitary model. In particular, when this lower bound, so what happened in this lower bound? So this one is famous as a model. And I will focus on to explain what is the Ising model next time. Okay, let's stop here. And if you have questions, just tell me. Except the unitarity.